Undecayed particle present at time t. Present original is original t, the time for decay. Lambda, the decay constant. Lambda is the decay constant. Okay, let's see. Half life. So half life. Half life. Half life. Half life is the time taken for the activity of a radioactive sample to drop half of its original value. It means that if originally we have 100%, after a time, let's say time t, this 100% will drop to half of its original value. That is half of 100 is 50. So after t, we're going to have dropped to 50%. This time t is what we have life denoted as t halves. So at t equals to t halves, 100 dropped to 50%. So that's the meaning of half-life. Half-life is simply the time taken for the activity of a radioactive sample to drop half of its original value. So, what's the formula for half-life? So, half-life, T half is equals to ln 2 all over lambda. When lambda here represent the decay constant, we can also make lambda the subject of the formula. So, lambda can also be, lambda is ln 2 all over T half. So we can also have lambda. Lambda is ln 2 all over T half. So in this case, we're going to take some examples. So example, then exercise. Example. 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 They have life. They have life of radioactive. They have life of radioactive sodium is 24 days. Calculate the time taken. Calculate the time taken for a sample of sodium to decay 15% of its original value. To decay 15% of its original value. So I'll read back the exercise for everybody. The exercise goes thus. The half-life of a radioactive sample, radioactive sodium is 24 days. Calculate the time taken for a sample of sodium to decay 15% of its original value. So, solution. We have been asked to calculate the time, so we'll use our decay equation. The decay equation is given by Nt is equals to N0 e to the minus lambda e to the minus lambda t. So we have to make t the subject of the formula. So we are going to do ln on both sides because the ln function will cancel the exponential function. So divide through by n0 first of all. Dividing through by n0. N0 cancel. It means that e to the minus lambda t is equals to ln nt on n0 is equals nt on n0. To remove the e function, we apply ln, the natural logarithm. So ln, we'll put ln on both sides. So the ln cancel the exponential function. We're left with minus lambda t is equals to ln nt on n0. So t is equals to minus 1 all over lambda ln nt on n0. So that is the expression for the time t. So t is equals to minus 1 over lambda ln nt on n0. Then, but we have lambda. Lambda is appearing in our expression. But remember what I told you guys. I told you that t half is equals to ln 2 all over lambda. That's a formula I gave you earlier. From here now, we can make lambda the subject of the formula. So lambda is equals to ln 2 all over t half. So the exercise will go in two phases. The first point, you have to look for lambda. Oh, look for lambda now, will come, will replace the equation. Then what is nt? What is n0? Originally, if we are talking about percentages, originally n0 is 100. But as time is passing, the 100 percentage keep on decreasing until it's going to reach 15%. So the question is asking us to calculate the time taken for which to drop from 100%, which is n0, to 15%, which is nt. So in the equation, let's remove our data. Nt in this case is 15%. N0, they have not given N0, but you yourself, you need to know N0. Knowing that it's percentages, know that the sum of all the percentages is 100. So it means that N0, initially, N0 is 100%. So N0 is 100%. They gave us a half-life. T half is 24 days. So those are the ingredients that have been given to us. So we'll first of all have to look for lambda. After looking for lambda, now we'll replace lambda in this equation. So let's look for lambda first. Let's look for lambda. Lambda is equals to ln 2 all over t half implies lambda is ln 2, t half is 24. Lambda is the punch of our calculator. The punch ln 2, sorry, ln 2 divided by 24. And our lambda is 0.029. That's lambda. We can replace now in this equation. So t is equals to minus 1 all over 0.029 ln 15 divided by 100. So punch by 15 divided by 100. Answer ln of 0.15 times -1. That is it. Divided by 0.029. So we have 64 point. T is equals to 65.4 days. So that's the time taken for the radioactive sample to drop from 100 to 15%. I've used the decay equation. So I'll see example 2. Example 2. Example 2 is less strenuous than example 1. There are shortcuts that we can use to avoid using the decay equation. So I'll show you how to avoid using the decay equation, but it has its own limitation. So I'll give you this method 2 and a limitation of method 2 so that you know what to use, when, and how. Example 2. the half-life of iodine 131 is 600 seconds. Calculate the time taken for a sample to drop to 1/16 of its original value. 1/16 of its original value. So we have to calculate the time taken for radioactive sample to drop 1/16 of its original value. So in this case now we want to solve this equation. In this case, we'll be giving fractions. We'll not be giving now percentages. But the whole number of a fraction is 1. Originally, we have 1. After 1, it keep on it fragmentates itself to give other fractions. In this case, we are going to avoid now the decay equation. To avoid the decay equation, originally we are having n. After, because they gave us a half-life 600 seconds. After 600 seconds, it goes to n on 2. N on 2 means half of n, which n is. Remember the definition of half-life. Half-life is the time taken for the activity of a radioactive sample to drop half of its original value. In this case, after 600 seconds again, it goes to n on 4. After 600 seconds, it goes to n on 8. After 600 seconds, it goes to n over 16. So we're going to stop here because the equation is telling us to stop at the level of 1/16. So in this case now, we're going to actually add the time up. So the time will be t is equals 1, 2, 3, 4. So having 4 times 600 seconds. So t is equals to 24.00 seconds. So I've avoided to use the decay equation. This one is less strenuous and is straight to the point than to use the equation nt is equals n0 e to the minus lambda t. But this exercise, this method of solving have a limitation. Why? Because imagine they're asking you to calculate the time taken to draw from 1 to, let's say, 25. In this case, it's simple because after 100, we can have 50. After 50, we'll have 25. So then imagine they ask you, okay, the time taken for you to draw 100 to like 10%. So let's do the decomposition and see. It's going to be 100. Half of 100 is 50. Half of 50 is 25. Half of 25 is 12.5. You see that 10 does not appear in this sequence of value. That's why this method cannot be used for this type of exercise. It's impossible. Why? Because 10 does not appear. Because after this will be 6.25. 10 is not appearing in this sequence of values. It's impossible. So it's usually advisable to use the decay equation because the decay equation cares less of if 10 is appearing or not. So our decay equation nt is equals to n0 e to the minus lambda t. So that t, we can have a formula of t. You're not obliged to prove the formula of t at any time t. So you can just say t is equals to minus 1 all over lambda ln nt all over n0. So that's their t formula. In this case, you know lambda. Lambda is ln 2 all over t half. If you ever calculate your lambda, when you have your lambda, you substitute in this decay equation. So that t is equals to negative 1 on lambda ln nt on n0. So that is all about lesson 2. So lesson 2 was talking about Radioactivity was still there for 2 lessons, which is quantum numbers and electronic configuration using the SPDF notation. Okay, we're going to continue with our chapter of today, and we're on lesson 3, quantum numbers. Lesson 3. Quantum numbers. There are 4 main quantum numbers. So we have the principal quantum number. So the principal quantum number. The principal quantum number. The azimuthal. Azimuthal. The magnetic. The magnetic. And the spin. So these are the 4 main quantum numbers we are going to see in these lessons. So go to the straight to the point. We'll see 1, the principal quantum number. Principal quantum number. 1. The principal quantum number. The principal quantum number. N. The principal quantum number N here indicate the shell in which an electron is formed. So the shell stands from the K shell. We're having 4 main shells. We have the K shell, L shell, M shell, N shell. The number of electrons in the shell is given by 2n squared, where n is the principal quantum number. But in this case now, for a K shell, n is equals to 1, n equals to 2 for the L shell. For the M shell, n is 3,